For 6 years, the summit of Kīlauea has been carrying out one of the most extraordinary volcanic recoveries ever documented in modern geologic monitoring. Inside the volcano's vast summit caldera, elevation measurements reveal that the crater floor has climbed by more than 1,600 feet, or more than 500 meters, since the catastrophic collapse associated with the major 2018 eruption. The change has not produced a towering new mountain visible from across Hawaii's Big Island. Instead, it has unfolded inside the volcano itself, where repeated eruptions have been slowly rebuilding terrain that was violently destroyed when enormous quantities of magma drained away from the summit during one of the most consequential eruptive events in recent Hawaiian history. Few volcanic systems on Earth are monitored with the same level of precision as Kīlauea. Satellite measurements, laser mapping, thermal imaging, seismic instruments, gas monitoring stations, and repeated topographic surveys have documented the transformation in remarkable detail. The numbers alone are difficult to ignore. In May 2020, portions of the crater floor stood at an elevation of approximately 518 meters, or 1,699 feet. By May 19, 2026, those same areas had risen to approximately 1,026 meters, or 3,336 feet. The difference amounted to roughly 508 meters, or 1,667 feet, of vertical recovery inside the caldera in only 6 years. That scale of uplift is almost without precedent in a volcanic summit environment undergoing continuous reconstruction after collapse. The process has effectively reshaped the geometry of the caldera through repeated lava accumulation, layer upon layer, episode after episode. The recovery has become so substantial that researchers and volcanic observers are now attempting to estimate when the summit depression might regain the volume it possessed before the devastating collapse sequence of 2018 permanently altered the volcano's summit landscape. The origin of this dramatic transformation traces directly back to the events that began during early May of 2018. At that time, magma stored beneath Kīlauea's summit began migrating rapidly eastward through the volcano's extensive rift system. The molten rock traveled more than 24 miles, or approximately 39 kilometers, beneath the island before erupting in residential areas near Leilani Estates, within the lower east rift zone. Over subsequent months, lava erupted from roughly 24 fissure vents distributed across the region. As magma evacuated from beneath the summit reservoir, pressure support inside the volcano decreased dramatically. The summit could no longer sustain the overlying rock mass. Large sections of the caldera floor collapsed downward in repeated structural failure events as the underground void expanded. Instead of a single instantaneous collapse, the summit underwent a prolonged sequence of subsidence episodes that progressively deepened and widened the crater complex. The resulting collapse fundamentally changed the morphology of Kīlauea's summit. A new caldera formed inside the older summit depression, creating steep walls, unstable scarps, and an enormous basin left behind by the withdrawn magma. Scientists later estimated that the summit collapse involved a volume change of approximately 836 million cubic meters of material. To visualize the scale, that amount would occupy a volume capable of burying entire urban districts beneath hundreds of feet of rock. The collapse itself represented only one part of the larger geologic process. At least a similar volume of magma, and likely more, was simultaneously transferred into the East Rift Zone, where it fueled the destructive eruption that transformed large portions of the lower Puna region. Lava inundated neighborhoods, highways, forests, and agricultural land while continuously erupting for months. The summit collapse and lower East Rift eruption were directly linked components of the same magmatic drainage event. By the conclusion of the 2018 eruption, Kīlauea's summit bore little resemblance to the landscape that existed beforehand. Areas once occupied by the former Halemaumau lava lake had disappeared into a massive pit. Cliffs towered over the newly deepened crater floor. Structural instability remained widespread. Portions of the caldera walls continued adjusting to the enormous stress redistribution produced by the collapse. Yet the rebuilding process began surprisingly quickly. Within the years that followed, magma gradually returned to the summit reservoir system beneath Kīlauea. Renewed eruptions inside the caldera started depositing fresh lava onto the crater floor. Every eruptive episode added another layer to the growing accumulation. Instead of carving downward, the volcano began filling upward. Through 2020, 2021, 2022, 2023, 2024, 2025, and into 2026, repeated summit eruptions steadily elevated the caldera floor. Lava ponds formed and solidified. Crusts fractured and resurfaced. Fountains sent molten rock high into the air before it spread outward across the depression. New flows buried older surfaces, gradually smoothing portions of the once chaotic collapsed terrain. Measurements collected over that period indicate that since December of 2020 alone, Kīlauea has erupted an estimated 502.1 million cubic meters of lava into the summit region. That quantity is enormous by any volcanic standard. It represents enough material to fill more than 200,000 Olympic-sized swimming pools. More importantly, it accounts for approximately 60% of the estimated volume lost during the summit collapse of 2018. The implications extend beyond simple statistics. The data demonstrate that Kīlauea is actively rebuilding substantial portions of the summit structure at a pace far exceeding what many volcanic systems achieve after major caldera collapse events. In geologic terms, the recovery is occurring almost instantaneously. Particularly significant acceleration occurred during episodic lava fountaining events that began on December 23, 2024. During these eruptions, fountains of lava repeatedly surged upward from summit vents, distributing large volumes of molten material across the crater floor in relatively short periods of time. Observations showed that since the onset of these eruptive episodes, portions of the caldera floor have risen by approximately 97.2 meters, or about 319 feet. That amount of uplift in such a short interval illustrates the immense eruptive efficiency of Kīlauea's summit system during sustained magma supply conditions. The volcano is not merely erupting continuously. It is delivering enough material to substantially alter summit topography within months. Researchers examining the refill process have increasingly focused on whether the summit caldera could eventually regain approximately the same volume and elevation it possessed before the 2018 collapse. To address that question, analysts have developed mathematical trend projections based on observed lava effusion rates, eruption frequency, and cumulative erupted volume. Some projections indicate that the caldera may return to near its pre-collapse volume around late December 2028. Other modeling approaches produce a broader range extending from approximately late 2027 into early 2030. These projections are based on regression analyses that incorporate both eruptive periods and intervals of volcanic quiet. Rather than assuming uninterrupted lava output, the calculations attempt to account for the fluctuating behavior typical of basaltic shield volcano systems. Even so, the forecasts remain highly sensitive to changes in eruptive activity. Kīlauea is not a machine operating at constant output. The volcano responds dynamically to magma supply, conduit pressure, structural adjustments, and regional stress changes throughout the Hawaiian hotspot system. A prolonged pause in summit eruptions lasting several years would significantly delay the refill timeline. Conversely, an extended period of vigorous lava fountaining could accelerate the process beyond some projections. Another important factor involves the geometry of the caldera itself. The floor of the collapsed summit depression does not rise evenly in all directions. Portions slope downward toward the eastern side of the caldera. Because of that topography, lava could potentially overtop sections of the 2018 collapse rim before the entire depression becomes completely refilled. In practical terms, some areas may reach or exceed former summit elevations earlier than others. The summit's rapid reconstruction has also highlighted the extraordinary magma transport efficiency within Kīlauea's plumbing system. The Hawaiian volcano is fed by the mantle plume underlying the Pacific plate, where partially molten material rises from deep within Earth's interior. That magma ascends into shallow storage regions beneath the volcano before migrating through fractures and conduits toward eruption sites. During the 2018 crisis, the summit storage system lost pressure so rapidly that the overlying caldera structurally failed. The fact that the volcano has since replaced more than half of the lost volume in only several years demonstrates that magma recharge into the summit reservoir has remained substantial. This process has unfolded alongside persistent seismic activity and continuous deformation throughout the summit region. Instruments positioned around the volcano routinely detect earthquakes associated with magma movement, pressure fluctuations, and structural settling. Inflation and deflation cycles repeatedly alter the summit surface as magma accumulates beneath the volcano and later erupts onto the crater floor. Each eruptive episode effectively becomes part of a larger construction sequence. Newly erupted lava spreads across the caldera floor while still molten, then gradually cools into solid basalt. Over time, additional eruptions bury those flows beneath fresh layers. The resulting accumulation thickens progressively, elevating the crater floor and reducing the overall depth created during the collapse. Thermal imagery has documented extensive heat retention within many of the newer lava fields. Even after surface crusts solidify, molten material often remains insulated below. Fractures can reopen unexpectedly as lava drains or pressure redistributes beneath the hardened exterior. The summit therefore remains a highly dynamic environment, despite the apparent stability visible from distant observation points. The transformation of Kīlauea since 2018 also demonstrates the cyclical nature of shield volcano evolution. Hawaiian volcanoes repeatedly undergo phases of magma accumulation, eruption, collapse, rebuilding, and structural adjustment over geologic timescales. The events currently unfolding at Kīlauea provide scientists with an unusually detailed real-time example of those long-recognized volcanic processes. Historically, caldera collapse events have occurred multiple times during Kīlauea's evolution. Geological records preserved in lava layers and summit deposits indicate that earlier summit depressions formed and later refilled repeatedly across centuries and millennia. The present refill phase therefore represents another chapter in the volcano's continuing structural evolution, rather than an isolated anomaly. Still, the pace of the modern recovery remains remarkable because of the precision with which it can now be measured. Earlier generations lacked the satellite radar systems, drone surveys, continuous laser mapping, and high-resolution topographic models available today. Modern monitoring allows scientists to track elevation changes down to fine scales across broad areas of the summit. Those datasets reveal that Kīlauea's refill process is not occurring uniformly. Certain portions of the crater floor rise faster depending on vent locations, lava flow distribution, eruption duration, and localized ponding behavior. Some areas accumulate thick stacked lava deposits while others remain comparatively lower. Over time, the internal topography continues evolving as fresh eruptions redistribute molten material throughout the summit basin. Lava composition also plays an important role in determining how rapidly the caldera fills. Kīlauea typically erupts basaltic magma characterized by relatively low viscosity compared with more silica-rich volcanic systems. Because the lava remains fluid, it can travel efficiently across the crater floor before cooling. That mobility allows eruptive episodes to cover large areas relatively quickly. In more viscous volcanic systems, erupted magma may pile near vents and form steep domes instead of extensive lava sheets. Kīlauea's basaltic behavior therefore favors broad infilling of the caldera rather than isolated accumulation near eruptive fissures. The volcano's eruptive style directly contributes to the rapid elevation increases now being documented. At the same time, the rebuilding process introduces new structural complexities into the summit environment. Layers of fresh lava cool and contract as they solidify, producing extensive fracture networks. Beneath the surface, residual voids and lava tubes may remain partially molten for extended periods. Differential cooling can generate instability in portions of the newly formed terrain. Repeated inflation and deflation cycles further complicate the summit structure. When magma accumulates underground, the surface may swell upward slightly. During eruptive episodes, portions of that pressure are released. Over years, these cycles interact with the growing lava accumulation to continuously reshape the summit region. Gas emissions remain another critical component of the volcanic system. Kīlauea releases substantial quantities of sulfur dioxide, carbon dioxide, water vapor, and other volcanic gases during eruptive activity. Gas release rates often fluctuate alongside changes in magma movement and eruptive intensity. High sulfur dioxide emissions in particular can contribute to VOG, the volcanic haze that periodically affects air quality across portions of Hawaii. The continuing refill of the summit caldera also carries broader implications for future volcanic behavior. As the summit geometry changes, pressure conditions within the volcanic plumbing system may evolve as well. The growing lava accumulation alters weight distribution across the caldera floor while changing the configuration of eruptive pathways and lava storage regions. Whether future eruptive activity remains concentrated at the summit or migrates once again into the East Rift Zone depends on evolving subsurface conditions that are not directly visible. Magma transport pathways can shift as fractures open, seal, or reactivate beneath the volcano. Kīlauea's history demonstrates repeated transitions between summit eruptions and rift zone activity over time. The lower East Rift eruption of 2018 illustrated the destructive potential associated with large-scale magma migration away from the summit. When magma drained eastward, the summit collapsed because the supporting reservoir rapidly emptied. The ongoing refill process therefore reflects not merely surface lava accumulation, but also broader restoration of magma storage beneath the summit itself. One of the more striking aspects of the current recovery is the narrowing range of refill forecasts over time. Earlier estimates produced much wider timelines extending several additional years into the future. As more eruption data accumulated and eruptive behavior became better constrained, trend models gradually converged toward a narrower range of likely refill dates. That increasing precision reflects the value of long-term monitoring datasets. Every eruptive episode provides additional information regarding lava output rates, eruption intervals, and magma supply behavior. Researchers can incorporate those measurements into updated regression models that improve future projections. Even so, forecasting volcanic behavior remains inherently uncertain. Kīlauea has repeatedly demonstrated the ability to transition abruptly between eruptive phases. Periods of relatively stable summit activity may be interrupted by rapid changes in magma transport or eruptive location. Structural adjustments inside the volcano can alter conduit efficiency and pressure relationships in ways that are difficult to predict precisely. The volcano's recent history illustrates this variability clearly. Following the dramatic collapse of 2018, portions of the summit later hosted a growing lava lake before renewed eruptive episodes spread additional flows across the caldera floor. Activity intensified again during episodic fountaining phases beginning in late 2024. Each stage contributed differently to the overall refill process. Satellite radar interferometry has proven especially valuable in documenting these changes. By comparing repeated radar measurements collected from orbit, scientists can detect subtle elevation variations across the summit surface. These techniques provide high-resolution maps showing where uplift is occurring most rapidly and how deformation patterns evolve through time. Drone-based photogrammetry and airborne LiDAR surveys have also supplied extremely detailed topographic models of the summit region. Those measurements allow researchers to calculate changing lava volumes with far greater precision than was possible during earlier decades of volcanic observation. The resulting datasets reveal a volcanic system rebuilding itself in real time. Areas that once represented deep collapse pits are gradually becoming elevated lava plains once again. Steep scarps formed during the collapse are being partially buried by accumulating flows. The summit landscape visible today already differs dramatically from the terrain observed immediately after the 2018 eruption. Yet despite the enormous amount of lava already erupted, the caldera still retains substantial remaining volume to refill. More than 300 million cubic meters of missing material remain based on current estimates of the 2018 collapse deficit. Achieving complete recovery to pre-collapse geometry therefore still requires sustained eruptive activity over additional years. That continuing reconstruction underscores the immense scale of volcanic processes operating beneath Hawaii. Even after erupting hundreds of millions of cubic meters of lava since 2020, Kīlauea continues receiving enough magma supply to maintain repeated summit activity. The energy involved in transporting and erupting such quantities of molten rock remains staggering. At deeper levels, the Pacific Plate continues moving northwestward across the Hawaiian hotspot, where mantle-derived magma rises persistently from Earth's interior. Kīlauea represents one expression of that hotspot activity, channeling magma through a complex volcanic system that has evolved over hundreds of thousands of years. The summit refill now underway serves as a visible reminder that volcanic landscapes are never truly static. Features that appear permanent on human timescales can transform dramatically within only a few years when magma supply conditions change. Entire crater floors may collapse, then rebuild again through persistent eruptions. In Kīlauea's case, more than 1,600 feet of vertical recovery inside the summit caldera within 6 years ranks among the most extraordinary examples of rapid volcanic reconstruction documented in the modern era. The numbers continue increasing with each eruptive episode. Every new lava flow adds another layer to the rebuilding summit. Whether the caldera regains its former volume by late 2027, 2028, 2029, or later will ultimately depend on the behavior of the magma system beneath the volcano. Continued eruptions could steadily erase more of the collapsed depression. Extended pauses could slow the recovery substantially. Future structural adjustments may alter the process in unexpected ways. For now, however, the trend remains unmistakable. The summit depression carved open during the catastrophic events of 2018 is being rebuilt at extraordinary speed. Kīlauea is once again reshaping itself from within, elevating its crater floor hundreds of meters through the continuous accumulation of fresh basaltic lava. Across Hawaii's Big Island, one of Earth's most active volcanoes continues demonstrating the immense capacity of volcanic systems to destroy, rebuild, and transform landscapes on timescales measured not in geologic ages, but in years.